So, we're moving into Chapter 4. So we start off Chapter 4 talking about electron configurations. We ended Chapter 3 talking about electron configurations. We just kind of blew through them, and many people think, oh, well, that was just not enough for me to understand anything. That's right, because we continue to cover them in Chapter 4. So when we're talking about electron configurations, what we're talking about is the stability of the atom. A stable electron configuration means that the chemical will... Oh, I'm so sorry. The chemical will then be stable. So, what determines if a electron configuration is stable or not? Well, what we call the outer shell of electrons is valence electrons. Everything inside the outer shell is called a core electron. If you remember, I told you the difference between an excited and a ground state is a ground state can only have openings in its outermost shell. It can only have valence openings. A excited state will have core vacancies, where an electron is not where it could be inside of a core shell. Noble gases have a completely full valence shell, or more appropriately, they have a completely empty valence shell. Two different ways of describing it, but either way, the outermost shell that has electrons in it has all the electrons it can possibly have. What that means is that noble gas doesn't need to react to gain or lose electrons in order to be stable. It is stable exactly as it is, which is why they're called noble gases. And you may think, I have no clue what he's talking about. Yes, you do. Neon, for example, is a noble gas. You can pass a very large amount of electricity through it, and it won't react. And the reason why it won't react is because neon is non-reactive because it is a noble gas. Helium is a noble gas, neon, radon, all of these are noble gases. And the reason why they're non-reactive is because they have, depending on how you want to describe it, either a completely full or a completely empty valence shell. Everything else will want to either lose or gain electrons to get to that state where it has a empty or full valence shell. This also helps differentiate between metals and nonmetals. Everything that is a metal is something that wants to lose electrons in order to become positively charged to achieve a noble gas electron configuration. Anything that wants to gain electrons and become negatively charged in order to form a noble gas electron configuration is considered a nonmetal. And if you look at your periodic table, there's a line going in between the metals and the nonmetals, and anything touching that line is actually called a metalloid. I'm so sorry. Anything touching that line is actually called a metalloid. It has some properties of metals and some properties of nonmetals. So if we look at the first two rows of the periodic table, you have hydrogen, you have helium, you have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. Helium and neon both being noble gases because their outer valence shell is completely full or completely empty, depending on how you want to look at it. For the rest of the class, I will refer to that as completely full because to me that's how I was taught and that's how it makes more sense. What you see here is called the Lewis dot electron configuration. So what you're showing in the Lewis dot electron configuration is the valence shell of each individual atom. So what you see here is hydrogen has one valence electron because it's got one electron overall. If it gains one electron, or loses one electron, or shares one electron, all of those situations, it becomes a noble gas configuration. Now, hydrogen is much less likely to lose an electron because it is all the way on the left side of the periodic table, and everything on that side is considered a metal, and it wants to lose, except for hydrogen. Hydrogen is this really weird thing where it doesn't fit the preconceived notions. Hydrogen wants to share or gain. And I have that wrong. Share or lose. All the other metals will almost all of the time lose. Hydrogen is one of the few metals that will actually share electrons. So when we get to sharing, you'll understand a lot more about what I'm saying. See, this is how this works. I give you little nuggets of information, and then I build on some of those, and then we come back around and you see how the other little nuggets of information can be used to build a bigger picture. So, some of you are confused already. Hydrogen has one electron. It can either share that electron or give that electron away. If it gives the electron away, it becomes hydrogen plus. It's lost a negative charge, so it becomes positively charged. Helium has two electrons. The 1s, or the one shell, can only hold two electrons. So with two electrons, helium's one shell is completely full, and its two shell is completely empty. So it is a noble gas. Lithium has 1s2 and 2s1. It has one electron in that second s orbital, in that 2s orbital. This means that it has one valence electron, which is what we show in the Lewis dot. It has one valence electron, which is what we're showing here. Beryllium has 4 total electrons, but only 2 of those are in the valence shell. The other 2 are in the first shell. So those 2 are in the first shell. Those are core shell electrons. These 2 are in the valence shell. They are valence shell electrons, and that's what we show on beryllium. If we were to draw the electron configuration for beryllium, it would be 1s2, 2s2. The 2 shell is not completely full or completely empty, because it can still hold 6p electrons in the 2 shell. So, beryllium has 2 valence electrons. Boron has 3 valence electrons. Carbon has 4 valence electrons. Notice how carbon, each one of those electrons, is alone. It's by itself. That is because the way electrons work in an atom, they will want to be unpaired most of the time. They all want to be unpaired, and then they start to pair up. Notice how in nitrogen you have your first pair. Oxygen, you have 2 pairs and 2 lone electrons. Fluorine, you have 3 pairs, 1 lone, for a total of 7. Fluorine has 7 valence electrons. Neon has 8 valence electrons. Neon has 10 total electrons. At this point, neon has a full outer shell, because the 2 shell can hold 8 total electrons. So, it's happy, it's satiated. I will use anthropomorphic terms from here on out. If you hear me talking about happy and sad, that's just the easiest way to describe these atoms. So, neon is happy. It doesn't need to lose or gain electrons, so it is a noble gas. What we will do, the first thing we'll talk about, is ionic bonds. Ionic bonds is when something that's a metal has electrons to lose, and something that is a non-metal has electrons that it needs to gain, will interact with each other. The metal will give away its electron, the non-metal will take that electron. That makes the metal positively charged and the non-metal negatively charged. Once you have that positive and negative existing side by side, they will attract each other together. So this is how we show this in picture form. That electron leaves, see if I can come up here and you can see it. Yep. That electron leaves that sodium and comes over here and interacts with this chlorine, making a chlorine negative and a sodium plus. These two then have an ionic bond with each other and want to interact. Much like North Pole and the South Pole of a magnet will attract each other, a positive and a negative in nature will attract each other. And so it makes sodium chloride, which is a salt. This is actually the chemical formula for table salt. And this is called an ionic bond. Anytime a charge separation occurs, where electron is lost from one thing and gained by another, that is called charge separation. Anytime charge separation occurs, it's an ionic bond. Your book has this as a picture. It's a really pretty picture. It's easy to understand. You have sodium with 11 electrons, chlorine with 17 electrons. Sodium wants to have a full shell because it wants to be in a noble gas configuration. If you look at sodium plus, that has the same electron configuration as neon. I'll let you work out those two electron configurations on your own. Work out the ground state electron configuration of sodium and the sodium plus and the ground state of neon neutral, and you'll see that they're the same. Chlorine minus has 18 electrons. It has the ground state configuration of argon. And so you can actually work out the ground state configuration of argon and the ground state configuration of chlorine minus, and you'll see that they're the same. The reason why is because once it has taken on that ionic form, it has taken on the noble gas electron configuration, which is why it's stable, and it's happy that way. We have a couple of terms to describe. So we have ionic. Ionic is the loss or gain of electrons in order to form charged ions, which bond in order to yield neutral compounds. This is important. In nature, you will always want to have neutral overall compounds. Charged compounds do not exist stably in nature. So if a charged ion forms, it wants to be paired with a charged ion of the opposite charge in order to yield a neutral overall compound. The octet rule was originally named when they thought that all valence shells had 8 electrons in them. That's ended up not being the truth, but it maintained that name. All atoms want to form stable electron configurations represented by the noble gas configuration nearest to their original configuration. That's what I said, with sodium plus being nearest to neon and chlorine minus being the same as argon. An atom will want to form an electron configuration that is the same as its nearest noble gas. So it will lose or gain electrons in order to form that configuration. A cation is a positively charged ion, and an anion is a negatively charged ion. Easy way to remember that: cat has a T in it. T looks like a plus sign. Anion is a negatively charged ion. Anion. Okay, what we have shown you there for sodium chloride is called a binary ionic compound. Binary meaning 2, ionic meaning that it has ionic bonds, compound meaning that it is overall neutral. So, what do we talk about when we talk about a generic binary ionic compound? We will have some cation, represented by X, will have A plus charge, and there will be M numbers of that atom in the compound. We'll also have a Y anion with a B minus charge, and there will be N numbers of that anion. The idea here is A times M is equal to B times N. What that means, the total negative charges across all of the atoms in a binary ionic compound, across all the anions in a binary ionic compound, need to be equal to all of the positive charges in the cation of the binary ionic compound. Now, I'm explaining this way because I'm going to use some examples, and I want you to understand what we're doing here. This is the formula for a binary ionic compound. You do not list the charges. You only list each cation and anion and how many of each there are. How do you get this information? Well, for most cations, you will either be told the charge or you will be able to know the charge. For most anions, you will be able to know the charge. If you take A and you move it to N, and B and move it to M, and then make them the lowest ratio between those two numbers, you will get the formula of the binary ionic compound. We're going to practice this more, so don't feel like you have to understand this right now. I'm explaining it to you, then we're going to go back and practice it. When you do that cross multiplication there, that works as long as A and B are not divisible into each other and A and B are not divisible by the same number. If they are, then you reduce that ratio. What you're trying to come up here is a ratio of the cations to the anions to where the total charge of positive and negative is equal. So if I have 2 atoms that both have a +1 charge, that is an overall +2 charge. If I have 2 anions that both have a -1 charge, that's an overall 2-. So then those would form a neutral compound. If I have 2 cations, both with a +1 charge, that's 2 overall positive charges. If I have 1 anion with a 2 negative charge, that is still an overall 2 negative charge. So then you would have 1 anion and 2 cations, and this is the ratio we're looking for. How many anions to cations? Okay, when you name a binary ionic compound, you name the cation and you name the anion. The cation, you add an ion to the end of it, and if the charge is variable, you add the charge. For the negative ion, you add IDE instead of the suffix. So, for example, oxygen, the suffix is EN. Actually, it's GEN. So it becomes oxide. For sulfur, the suffix of sulfur is UR, so it becomes sulfide. So let's form a calcium cation, and a sulfide anion will form CAS. And we'll go in and do more of that practice last class period. So, I've explained ionic bonds. Ionic bonds is where there's an electron transfer from one atom to another that creates a charge separation. This is, for your purposes, always between a metal and a nonmetal. It's not always true, but for the purposes of this class, we will constrain ionic reactions to nonmetal and metal. If you have covalent, co meaning together, valent meaning the valent electrons, what you're talking about there is both electrons have an electron, atoms have an electron that they share in between their two valence shells. So this electron is technically on both atoms at the same time. In this, there's a sharing of that electron. It can be shared unequally, and we call that polarity. But you will never in a covalent system have a complete charge separation. For your purposes, this will always be when a nonmetal binds with a nonmetal. There will be shared electrons. So let's talk about covalent bonds. The easiest covalent bond is hydrogen. So each hydrogen has one electron. Together they share those two electrons. Now, if an atom shares an electron with another atom, the other atom will share one electron back. If one atom shares two electrons, the other atom will share two electrons back. This is an equal thing. They have to be matched in order to share. The electrons, when they are shared, may not hang out on the two atoms the equal amount of time, but for every electron shared from one atom, there is an electron shared from another atom. So in this example, you have hydrogen. Each one of them has an electron. They share the two electrons together, and that creates what we call a covalent bond. Notice how instead of representing that as two dots, which are representative of two electrons, I represented that as a line between the two hydrogens. That represents that those electrons are shared between those two atoms and hold those two atoms together as a bond. It can be drawn either of these two ways, but the more correct way is to draw it the way the top is, where there is this line connecting the two, because a covalent bond holds atoms together. So if I have two oxygens, how would they form covalent bonds with each other? Well, if you think back, I showed you the valence electrons for an oxygen back when we talked about Lewis dot configurations a couple of slides ago. Each of these has 6 total valence electrons. Each one of these, in order to be happy, needs to see 8 total electrons. So the key with sharing is it wants to get to this octet rule, the nearest noble gas configuration. Oxygen would want 2 more electrons in order to be in that noble gas configuration. So it will share 2 so that it can then see 2. So each one of these oxygens shares 2 with the other, and it forms the double bond. So for every electron shared from either atom, a bond is formed. Because each of those oxygens shares 2 electrons, it forms 2 bonds. You get to where you can see that. Okay. So each electron shares, or each oxygen shares 2 electrons, and so it forms 2 bonds like that. Okay? So how would 2 oxygens and a carbon bond together? Well, carbon wants 8 total electrons. Oxygen wants 8 total electrons. In order for oxygen to see 8, it's going to need to share 2. In order for carbon to see 8, it's going to need to share all 4 of the electrons it has. So carbon donates 4, each oxygen donates 2, and what you have is you have double bonds between each oxygen and that central carbon. But it doesn't stay in this configuration that I have shown, because those electrons that are shared around that carbon atom want to get as far away from each other. Think of these electrons, and they are like little negative charges. They don't want to be any closer to each other than they have to be. Think of 2 magnetic souths or 2 magnetic norths. You get them close to each other and they repel each other. Same thing happens here. They repel each other to 180 degrees from each other, and it forms this stick molecule. When we get to the end of this chapter, we'll talk about molecular configurations, molecular shapes, and this is how we form those molecular shapes, is the repulsion of electrons from each other in covalent sharing bonds. So when we name covalent compounds, the first thing we do is we have a prefix that goes on every atom that is part of the covalent compound. That prefix indicates the quantity of that atom in the compound. So for example, the 2 oxygens and 1 carbon in that covalent compound would be dioxide and monocarbide. But monocarbon and dioxygen. Mono meaning 1 because there's 1 carbon, di meaning 2, there's 2 oxygens. So you put a prefix on each one of those to indicate how many. Then the first element suffix is not modified, but every single other one change it to look like a negative ion. So you've heard of carbon dioxide. That was what I showed you. It's more appropriate to call it monocarbon dioxide. Mono meaning 1, carbon, you don't change the first suffix. Then dioxide. You change it to oxide from oxygen because it is the second element in this covalent compound, so you change its suffix from GEN to IDE. So, when we talk about sharing, we have to talk about electronegativity. Electronegativity is unequal sharing of electrons. So think of electronegativity as how much each atom wants that shared pair of electrons to hang out around it. A really good example of this is it's an affinity for electrons for each atom, just like you could give a number of my affinity for cheeseburgers. I have a very high affinity for cheeseburgers. I'm going to try and take as many cheeseburgers as I can. Some people don't have a high affinity for cheeseburgers. They don't really want cheeseburgers, so they're going to give away as many as they don't need. They'll keep 1 cheeseburger because they need to have something to eat for dinner. I'll take like 17 cheeseburgers because I don't mind picking out on cheeseburgers. So it's an affinity for electrons in the same way that people have affinities for different foods. So electronegativity is how much an atom wants those extra electrons that are shared. It increases as you go from left to right and from bottom to top. So the most electronegative element is fluorine. The least an electronegative element is francium. When you know the electronegativity of different elements, you can actually calculate the polarity, or how much ionic nature they demonstrate in the covalent bond. How much partial charge separation there is in this atom. You will not have to calculate polarity. I will not give you electronegativity values and ask you to calculate polarity, but understanding what it is helps you understand how we describe these things. So, 2 hydrogens are going to have the same electronegativity because they're the exact same atom. So when they share electrons, those electrons are shared equally around the entire hydrogens. Lithium hydride, for reference, the lithium does not want the electrons as much as the hydrogen. So those electrons are going to be more on the hydrogen and less on the lithium. The lithium is the black ball there, hydrogen is the white ball. And you can see now that there's an unequal sharing of those electrons. The molecule is going to be more positive in that blue area and more negative in the red area. If you show hydrogen fluoride, which is another covalent compound, here the fluorine is that green atom, and the white is still the hydrogen. Here you can see that the electronegativity difference has flipped, and the fluorine has a much higher electronegativity than the hydrogen, so the hydrogen actually has a partial positive charge, and the fluorine has a partial negative charge. And here's electronegativities for some other polyatomics, such as ammonia, methane, water, and hydrogen fluoride again. You can see that there is a variety of different electronegativities based on the different covalent sharing. And in fact, there are two here that are nonpolar because the unequal sharing cancels out, or there is equal sharing. So here, the hydrogen, H2, is nonpolar because there is no unequal sharing. The methane, the Ch4, is nonpolar. There is unequal sharing between each hydrogen and the carbon, but if you think of them as little chains pulling on each other, all four of those hydrogens are pulling in opposite directions, and so they cancel out. Whereas all the others, it's not an equal pull in all directions, and so there is a polarity through the molecule. I mentioned polyatomics. Polyatomics are a group of two or more covalently bonded atoms. You will be expected to know the table of polyatomics that's on page 107. It's table 4.4. Polyatomics are treated as a simple anion or cation in a binary ionic compound. And so there will be some compounds on your test that have covalent bonding inside of a polyatomic, and then ionic bonding between that polyatomic and something else. Alright, when we describe different covalently bonded molecules, we will draw them as a Lewis formula. And here we show lines connecting the different atoms. And if there is an ionic charge, we show that with a bracket and a number indicating the ionic charge. And then lone pairs around an individual atom are shown as two dots. So any lone pairs shown as two dots around that atom, all shared electrons are shown as a covalent bond, a line connecting the two atoms that are sharing electrons with each other. And we will work on need has shared next week. So I will see you on Thursday.